Okay, we're going to do the notes for 5.2. So we're talking about one-to-one and inverse functions. So let's quickly fill in a definition here. So a function is one-to-one, and notice we're talking about only functions. So if I'm talking about only functions, remember what that means is it means that the graph passes the vertical line test, and it also means that if I were to look at a set of ordered pairs, none of the domain or none of the x's repeat. That's going to be important to knowing to what one-to-one is. So a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are different inputs into the function, then f is one-to-one if your f of x1 is not the same as your f of x2. Two different x's have to give you two separate y's. If you look at the picture, this first one is one-to-one because notice how each x simply goes to one y. This is not one-to-one because these two x's go to the exact same y. Can't happen in a one-to-one function. This one isn't one-to-one. It's not even a function because this x goes to two different y's. So if it's not a function, then it certainly can't be a one-to-one function. So what I like to do is I kind of like to look at it as ordered pairs. If we look at example 1, the question is, does this represent a one-to-one function? Well, if I write it as ordered pairs, Dan is paired with Saturn, so that's going to be DS. John goes with Pontiac, we'll go JP. Joe goes with Honda, oh shoot, we better go Joe H. And Andy goes with Pontiac. Andy goes with Pontiac. So it says determine whether they are one-to-one. So here's another way to think of one-to-one. Remember, if none of the x's repeat, it means it's a function. So if you look at this, you've got Danny, John, Joe, and Andy. Do any of the x's repeat? No, none of the x's repeat. So it's a function. If it is a one-to-one function, it means none of the y's repeat. Well, that is not true here because if you notice, this y repeats. Not only does John get matched with Pontiac, but Andy gets matched with Pontiac. So that means that this is not one-to-one. Again, one-to-one means none of the x's repeat and none of the y's repeat. Think of it that way. If I look at this set of ordered pairs, it's a function because none of the x's repeat, and in fact, none of the y's repeat either. So this is a one-to-one function. So remember I talked about 2 minutes ago that you can tell if it's a function if it passes the horizontal or the vertical line test. We've learned that. Not only is there something called a vertical line test, there's also a horizontal line test. So the horizontal line test, it works exactly the same as the vertical line. If every horizontal line intersects the graph of a function f in at most one place, then the function is one-to-one. So in other words, if you have a graph, if it passes both the vertical line test and the horizontal line test, it means that you are looking at not only a function, but a one-to-one function. Let's see that work. So here we go. Let's look at this picture. It is a function because it passes the vertical line test. Beautiful. Is it one-to-one? Absolutely not. Because, for example, if I draw a horizontal line right there, it hits the graph in two places. My goodness, if I draw a horizontal line here, it hits the graph in 1, 2, 3, 4 places. This is not one-to-one. How about this graph right here? It passes the vertical line test, absolutely. So it's a function. Does it pass the horizontal line test? It does. Since it passes both, this is a one-to-one function. Okay, so now we're going to start getting into something called the inverse function. Suppose f is a one-to-one function, so we start with a one-to-one. Then to each x in the domain of f, there's exactly one y in the range, because f is a function, and to each y in the range of f, there's exactly one domain. So we talked about that. That means one-to-one. Everything is mapped to one and only one thing going both ways. The correspondence from the range of f back to the domain of f is called the inverse. This is the symbol we use for inverse. And here's a note. Don't think of inverse as 1 over f. That's not what it is. And we're going to show examples of how to find the inverse. In other words, two functions are said to be inverses of one another if they are basically reverse process of each other, like addition and subtraction are inverses of one another because they undo one another. So let's look at functions in lots of different ways, and we'll talk about how to find the inverse. This is a one-to-one function. We already saw that on the previous page. We can see that the domain is 1, 2, 3, and 4, and the range is 5, 8, 11, and 14. Easy peasy. If I want to find the inverse, well, let's just quickly use the correct notation. So this is f. If we want to find f inverse, don't overthink this. You simply flip the domain and the range. How hard is that? That's all you do. You flip the domain and the range. So the domain of f becomes the range of its inverse. The range of f becomes the domain of its inverse. You flip the domain and the range. So that's basically what this says down here. If I'm looking at a mapping, the domain of f is equal to the range of f inverse, and the range of f is the domain of the inverse. So there's going to be a couple of different ways that we are going to look at these inverses. Let's look at this first one. Here's a fact, they call it, but it's very important for you to know. What f does, f inverse undoes, or does the vice versa. Therefore, if I want to find the composition functions, think of it this way. Whatever f does to that letter x, let's say it adds 2 or it subtracts 10, whatever f does to x, f inverse undoes what it just did. So if I start with x, f does something to it, and then f inverse undoes that, where do I end up? I end up at x. Same thing down here. If I compose, so think of it this way, if I compose, we did that in the last section, f and f inverse, I should always get x. This is how you verify that two functions are inverses of one another. You compose them both ways, and then you see if you get x both ways. We practiced that in the last section. We just didn't say what we were doing. So verify that G and what they call G inverse are actual inverses of one another. Maybe they're trying to fake us out by showing that if I compose them both ways, I'm going to get x. So let's do it. So let's find, first of all, G of G inverse of x. So in other words, I'm plugging my G inverse into my G. Plugging G inverse into G. Well, that's going to look like this. The cube root of x minus 2 cubed plus 2. Well, if I cube a cube root, the roots disappear. and gee whiz, I get x, but that's not good enough. I need to also go the other way. So now I need to find g inverse of g of x, which again, what does that mean? That means I'm going to plug my g into my g inverse. So let's see what that's going to look like. It's going to look like the cube root of x cubed plus 2 minus 2, which is the cube root of just x cubed, which is x, because I compose them both ways, g of g inverse and g inverse of g, and I got x in both cases. That means that I am looking at two functions that are inverses of one another. Well, now let's look at a graph. So first of all, a quick theorem. If I have a graph of a one-to-one function and I also graph its inverse on the same graph, they will always be symmetric with respect to the line y equals x. And remember, and I'm going to graph it on this graph we do, but remember y equals x is our identity function. It is the line that bisects the first and the third quadrant. So here they give me a silly looking function, and it's asking me, and by the way, it is one-to-one because it passes the vertical line test and the horizontal line test. It's asking me to then graph the inverse. So really all I have to do that is to take each one of the ordered pairs and flip the domain and the range. So for example, this point right here is at, it's at -1, 0. So on the inverse, I'm going to graph 0, -1. That is a point that's on the inverse. This point is 2, 1. I'm going to graph 1, 2. That is a point that's on the inverse. This point is -2, -1. I'm going to graph -1, -2. So if I kind of connect these points that I just graphed, there is my inverse. Now, show their inverses. Look, if I were to graph the line y equals x, that's again the line that bisects the first and the third quadrant. Notice the symmetry. It's like a mirror. The graph looks exactly the same. The two graphs look exactly the same as on the top as they do on the bottom. And that will always be true if you're talking about two inverses. Okay, so last page here. Let's quickly talk about how do I find an inverse? What's a procedure? Well, it's really a three-step procedure. First of all, in y equals f of x, so if I have a function f of x, the first thing that I do is I literally flip the domain and the range. I literally exchange the x and the y. So my y equals f of x becomes x equals f of y. Literally switch the domain and the range. If possible, then you solve the implicit equation for y in terms of x. So you flip the x and the y, and then you solve for y. If you solve for y, you're going to end up with its inverse. And then if you wanted to, we're not going to, but if you wanted to, you could always check to make sure you're right by finding f of f inverse of x and finding f inverse of f of x. And if they both turn out to be x, then you know that you are correct. Now, I'll be honest with you, that makes it sound a lot worse than it is. Let's just do two quick examples here. So we'll do an easy one first. This one, the algebra is easy. The bottom one, it's a little bit more difficult. So find the inverse. So remember, this really means y equals 4x plus 2. So I usually like to write it first that way. Now I'm going to literally flip-flop the x and the y. And now I'm going to solve this equation for y. So let's see, I would subtract the 2 and divide by 4. I found the inverse. The last thing that you want to do is put this into inverse notation. So take the y and change it to an f inverse of x, because that's the correct notation. And that is the inverse of my f of x. If I were to graph both of those lines, they're both linear, they would be symmetric with respect to the line y equals x. And you could check it if you wanted to. All right, the algebra in number 7 is a little bit more complicated because we're talking about a rational function. Okay, so here we go. By the way, notice it says the function f of x, it's a rational function, and it makes sure that you know that the domain is all x's except for -1, because we can't have a 0 in there. So now let's go ahead and let's find the inverse function. We're going to use exactly the same steps we did before. So I'm going to change the f of x to a y. Now I'm going to flip-flop the x's and the y's, exchange the domain and the range. So that would look like x equals 2y minus 1 over y plus 1. Make sure both x's become y's. Now we need to solve this for y. This is going to be a little bit more complicated, but I want to show you the steps. So let's go ahead and let's cross multiply. So that would give me xy plus x equals 2y minus 1. It's more difficult because notice we have y's in two different terms. So now what we want to do is we want to gather everything with a y to one side and everything without a y to the other side. Here's the key step. I want to solve this for y. I need to factor the y out of my two terms over here as a greatest common factor. And now if I want to get y alone, I would simply divide both sides